5.1, day 1, we're talking about logarithms. So the first thing you need to know is that a logarithm is actually the inverse of an exponential function. So inverse meaning that's the thing that undoes an exponential function. And you actually did these in Algebra 2, but here's the setup. So you have a number that's your base raised to an exponent, and whatever that value is, your output, you get an answer. And so when we use logarithms, so that's exponential form. When we use logarithms, we'll go to log form. You're going to have log, and then the number that was the base on the exponent, now that's the base on the logarithm. And then the green part, the answer, that goes here in parentheses. So log, the base of the answer is now equal to the exponent. And so this is logarithmic form. So this pattern is an important one to remember, because you're going to need to be able to switch back and forth between exponential form and log form. So I've got the pattern kind of color-coded here, but let's look at an example of going from exponential to log form. So let's say 3 squared, we know that's 9. So we have the equation 3 squared equals 9. And if we were to put that in log form, we'd have log, and then the base would be the base from the exponent, so log would be base 3. So if you look at that pattern, log is base 3, and then the answer actually goes inside the parentheses here, so log base 3 of 9 is equal to the exponent from before, so log base 3 of 9 equals 2. And you'll also need to go backwards from log form to exponential form as well. But as long as you have this pattern, as long as you're used to this pattern, you know it, you'll be good. Okay, next we're going to talk about the common logarithm. So common logarithm just says if y equals the log of x, and there's a log button on your calculator, it uses the common logarithm. Then 10 to the y is what x equals. So this actually uses the same setup we just talked about. But what's important for you to know is that if you don't see a number here on the logarithm, like there's no base here, it's implied that it's 10. So it's always understood. If there's no base on the logarithm, it's implied that it's just a 10 there. The base is 10. So 10 to the y equals x. We could just say log base 10 of x equals y. It's the same thing as log of x equals y. And then graphically, we can sketch a graph here. Just a general rough sketch. Y equals 10 to the x. So that's definitely exponential growth. So in exponential form, that's exponential growth. And then y equals log of x. So we said those were inverse functions. They're inverse operations. So you'll notice it's just a reflection of this graph. And what is that line that it's reflected over? If you remember back to inverses, that's the line y equals x. So y equals 10 to the x, that's exponential. And then y equals log of x, that's like log base 10. That's what's implied there. So they're inverses, so their graphs are just reflected over the line y equals x. And again, even if it's not written in there, you know it's implied that there's like a little 10, right? You know that that 10's there. Okay, so example 2, and it's got multiple parts. The directions are just to evaluate. So I'm going to have you evaluate some logs, which essentially means just come up with a value for them. So the first one, part A, is log of 100. So this value ends up being pretty simple, depending on how you look at it. So we know that If there's no number here on the base, we know that's just 10. And if we think about this in exponential form, our answer is really the exponent we're looking for, like 10 to what power gives you 100. So we write that out. We say 10 to what power, so the power is what we're looking for, so I'm going to go ahead and just write x. 10 to what power equals 100. 10 to what power gives us 100, right? So now it's probably obvious to you, but we had to go from log form to exponential form. We're looking for that exponent. So we know 10 to the second power is what gives us 100. Okay, the second one here, part B. Evaluate log of 1 over 10. And again, this is also a nice number. So how do you move forward from here? Well, you know there's a little 10 here, even if it's not there. On the log, there's a little 10. So we think about it as 10 to what power gives us 1/10. And maybe you already know, like you can think about it in your head. I'm going to use 10 to the x equals 1/10. And the best way to solve this is to make these bases match on both sides. So this is 10 to the x, and since this is 1 over 10, we can really write that as 10 to the negative 1. So now you can see how they match up. 10 to what power gives you 10 to the negative 1? So x has to be negative 1. Part C. What's the log of 1? So it's implied that that's base 10. So really what we're asking is 10 to what power gives you 1? So there's really only one possibility for x. There's only one exponent you can use that will give you an output of 1 in this case. And that will always be the 0 power. So anything to the 0 power equals 1. So how do we evaluate the log of 1? It's just 0. Part D, the log of negative 100. Okay, so I'm going to go ahead and think about, there's a base 10 on this, so there's a little 10 in there. So I want to know 10 to what power will give me negative 100. And if you're familiar with exponents, you know there's nothing you can plug in here. Even if you plug in a negative exponent, that won't make the output negative. That won't make the sign negative down here. So there's really nothing you could plug in for x that would give you negative 100. We know if you plug in 2, you get positive 100, but there's nothing you could plug in to get negative 100, so this one is not possible. You can't evaluate the log of negative 100. And more generally, you can't take the log of any negative number. Part E. This one's not a common logarithm. This one's log base 4 of 1 over 16. So right away you should notice that 4 and 16 are kind of related. So your answer is 4 to what power gives you 1 over 16. Okay? So if we write that out, 4 to what power, 4 to the x power gives you 1 over 16. Well, instead of calling this 1 over 16, I'm going to put that 16 up in the numerator. I'm going to call that 16 to the negative 1. So now I don't have a fraction there anymore. And at this point, I want to relate 4 to 16. So my goal at this point is I want to match the bases. So I want to get matching bases on both sides. And the easiest way to do that is to make 16 look like 4 to some power. So this one's 4 to the x. You can write 16 as 4 squared. So I want to get the same base on both sides, so I can write 4 to the x equals, and where 16 is, I'm just going to call that 4 squared. So now I definitely have the same base. And so since this is 4 to the power of 2 to the power of negative 1, let's just multiply those exponents. So that's 4 to the negative 2. So what do we have? Notice there's a match. 4 to something equals 4 to something. What has to be true? There's our answer. Those two green boxes have to be equal. So x equals -2. Okay, the final new idea for these notes, and this actually shouldn't be new, since we did in Algebra 2 also, the natural log. So here's the idea behind the natural log. We say if y equals the ln of x, which means the natural log of x, then e to the y equals x. So that's log form, and that's the exponential form. So what you should know about ln really means natural log, or natural logarithm, which is just a fancy way of saying log base e. So literally, like, the other way you could express this in logarithmic form would be log base e of x equals y. So when you see ln of x, you know that that's really just a fancy way to say log base e of x. So it is the same type of logarithm we've already seen, just it has a base of e. And remember back from last chapter, e is just a number, right? It's approximately 2.71. So that's the only thing different. It has its own special name, the natural log ln. Okay, graphically for this one, let's sketch the same type of graph. E to the x, since e is a number bigger than 1, it's definitely exponential growth. So if we graph y equals ln of x, since they're inverses of each other, it would reflect over the line y equals x. So y equals ln of x reflects over the line y equals x. They're inverses of each other. So e to the x and ln of x. We have two more examples related to natural logs here. So example 3, e to the ln of 5. We want to evaluate that. So right now this is definitely an exponential form. We have e to some power. So what I'm going to do is I don't really have anywhere to go at this point. I don't know what the ln of 5 is. That's some irrational number, some long decimal. So what I want to do is convert it to logarithmic form. So if you ever find yourself stuck in exponential form, convert it to log form, and vice versa. If you're stuck in log form, go to exponential form. So I'm going to set this thing equal to x, and you can set it equal to whatever you want. You can use y, you can use t, doesn't matter to me. I'm going to set it equal to x so that I can put this into log form. So that's just going to be log, and the base is going to be e, because e is the base from this exponent over here. So log base e, and then my answer should go here. So this should be x. Log base e of x is equal to whatever was in the exponent. So that's ln of 5. So far all we've done, e to the ln of 5, and this is going to be a nice number when we get done. We just set it equal to x so we can convert it to log form. Base e, the answer was x, the exponent was ln of 5, so that's my setup. Okay, now you should notice this. Since the log base e and ln are really the same, we could write it as log base e of x equals log base e of 5. And the important part about that, you should notice, log base e of this thing equals log base e of this thing. The green boxes here. We've got a match. So now our solution's obvious. X equals 5. Alright, and so for the final example, we're going to go the other way. I got ln of the cube root of e. Okay, so we know ln, that's just log base e, and we know the cube root, that's the same as the 1/3 power. So we have log base e of e to the 1/3. Okay, this is good, but now I want to convert to exponential form. So my answer is going to be e to what power would give me e to the 1/3 power. And that's probably obvious. You can hear it just by my voice saying it. But I'm going to set it up anyway. E to what power? So e to the x gives you e to the 1/3. Well, there's your match in the exponents right there. E to that thing equals e to that thing. The green boxes, they have to match, so in this case, x equals 1/3. So, a quick summary, logarithms. If you find yourself stuck in log form, convert it to exponential. If you find yourself stuck in exponential form, set it equal to x and convert it to log form. Alright, that's all for these notes. I'll see you in class.